It's a real pleasure to be here. I thank the organizers very much for having me. Today I'm going to be talking about climate models, which was the topic of some discussion earlier on. But I think I'll take it in a slightly different direction. Now this is a laser. There, that's a nice laser. Okay, this is green energy, by the way. This is the title of this talk is taken from Alice in Wonderland. And it is a response to Alice, who said that she found it difficult to believe in impossible things, and the Red Queen saying, well, it just takes practice, and I believed in as many as 6 impossible things before breakfast. I had this experience not long ago, well, a few years back anyway, where I was asked to explain myself to a climate modeler. I was telling a very theoretical kind of line of argument, and he wondered what good this was, what I was doing. His idea was that it wasn't useful for policymakers, what I was doing. And I said, well, what you do is useful for policymakers, what do you do? And he said, well, I solve the closure problem of turbulence regularly for policymakers. Of course, this is one of the big unsolved problems of science. And so immediately I thought of the Red Queen in that experience. So I'm going to tell you about this experience I have. Some people may know about the book I did with Ross McKittrick. And Ross McKittrick you probably know from his interactions with Steve McIntyre, who I also know, and very many interesting interactions with the two of them over the years. I could very easily I certainly saw their original hockey stick papers before they were released in manuscript form, and made some comments and so on. But that approach of talking about the internal consistency of what they're doing wasn't really my style. My question, I see that the whole hockey stick thing was wrong on so many levels, problematic on so many levels, that it was not my approach to it. So in Taken by Storm, which I did with Ross, this is the second edition, by the way. The first edition won a $10,000 prize. The second edition has a little bit of an account of the various struggles of Steve and Ross on the hockey stick. But our approach was a little different. This is a joke calculation that we did, where we used the same kind of general technique, and we used tree rings to figure out what the US GDP was back to the year 1000. And you can see it makes a perfect hockey stick. The interesting thing when you deal with humans is that they have an incredible ability to look at something that's completely preposterous and still try to figure out that maybe there's something to it. In fact, that's what happened. People said, well, maybe this is capturing some phenomenon in the United States back. And so it's when joking sometimes doesn't work. Anyway. But one thing we did do is in the second edition, we put in a foreword with a denouncement from a fake lord or knight of the UK. His name is Sir Mortimer Longbore, and we asked him, this imaginary character, to denounce the book. And so we write up this very typical denouncement based upon the standard forms. We think we do a better job than most denouncements. So the theory is that if you have the book pre-denounced, it's like having pre-shrunk blue jeans, so it fits perfectly. And so there have been a couple of times when it's been very helpful to me to point out, because a lot of people look at this denouncement on the front and they go looking up Sir Mortimer Longbore on the internet because they think that we're serious about this, but because it really follows the usual pattern, I still think we do a better job of denouncing it than most of the other people do. Anyway, I'm not really going to talk about that particularly. I'm going to talk really about climate models and how the climate problem is not an empirical problem, but a fundamental problem of fundamental research. But before I get into that, I also want to mention one sort of classic issue, which is the constant struggle of my life for the past 20 years or so, which is this problem of consensus, which of course is a really difficult thing for many people to comprehend. But this really encapsulated well in this cartoon where the committee here is saying then we're agreed that 9 to 1 that we will say our previous vote was unanimous. There's some things you can't vote on. The truth of something is just the truth, right? So that's one of the sort of big points. Now, I started getting into trouble in climate business long time ago. I built my first climate model in the 1970s. And one of the things I decided at that stage, I was in graduate school, I decided that I hated climate models. I thought they were just so weak and wobbly, and there were so many things that needed to be done. So I decided I'd go into more fundamental research. And so I said goodbye to that as far as I was concerned. But then I got this really nice postdoc at the Canadian Climate Centre, and with nice named postdoc and so forth. And it was with their general circulation modeling group. So I got to know all the insides of big climate models. And it was a great experience. I still have good memories of it. But one of the things they had there was they had this desire that they'd captured a theoretician and they were going to do some definitive things. So this is the early 80s. And they said they wanted me, a bunch of big wheels there sat me down in a room and they said, we want you to come up with the smoking gun that will prove global warming. And I thought about it and said, I don't think you can do that. And so then they said, well, what about this? And then I shot that down. And then they said, well, what about this? And then I shot that down. So I got into a lot of I got a little bit wrong-footed. And then Craig's father went and got into trouble about that time with something to do with a science paper and so forth. And I felt this kind of compulsion knowing about climate models to defend him. So I actually wrote this paper explaining why models couldn't really contradict exactly what he was said to be contradicting. And I got into a lot of trouble. So that was the first time I got into trouble in the climate business. And so it wasn't until about the 1990s when I resurfaced and things were getting out of control and I wrote a few little op-eds. And then finally, Ross McKittrick came to me and he said, look, Chris, I'd like to write a book and I want to get the physics right and so forth. And I said, well, I wouldn't do a straight book on this because this is all, well, it's Wonderland, okay? So I'll give you an idea of what Wonderland is like. Now, this is a test to decide whether you've been paying attention this morning. This is a quote which was actually put on the screen this morning by Fred. And it's a very extremist position in terms of climate. It's really the ultimate skeptic's position. It's even probably more skeptical than I'd like to be. And it's very, very extreme. And I put it to you, who is the author of this? Does anyone? The IPCC, yes, the IPCC. I give you the Intergovernmental Panel on Climate Change, the consensus position, welcome to Wonderland. You know, we will never be able to forecast climate. Then what's this whole thing about? You know, it's an interesting thing, and that just gives you a really clear idea of what we're dealing with. I mean, in the fourth assessment report, this stuff was all gone. Like you didn't really see it. It was kind of disappeared, shall we say? So you could see that one of the writers on the in this chapter probably is the equivalent of like help save me, I'm trapped in the IPCC, and this is the kind of thing that came out as a little warning, the old fortune cookie joke, Okay, so I always, when I do a talk on climate, I'm always interested in bringing up some goofy thing that some Wonderland type experience. So we have here, I mean, there are lots of examples. I mean, we've got carbon-free sugar. And, there's a wonderful video on this. You can find it on the net with Domino Sugar. There's a guy walking through the cane field and he's saying, wonderful news. We at Domino Sugar have now created carbon-free sugar. Oh, well, I mean, this is not the goofiest thing that I mean, there's like the death of the Loch Ness Monster, and there's all kinds of things like that. The lack of consensus among groundhogs, all these sorts of things that are available. But I didn't really want to get into those. I really wanted to talk about this because this really implies. This is a real campaign. This is Domino Sugar campaign that they have carbon-free sugar. Of course, what they mean is they mean carbon neutral. But this whole idea of being certified carbon-free is I suppose you could put silicone in there, and then it would become kind of an abrasive. You know, you wouldn't want to eat it, you know, but you know. Okay, so they mean carbon neutral. But then that also has a problem. What is this carbon stuff? Wasn't it about this vibration rotation spectrum? I mean, of carbon dioxide, the 15 micron band? You need those oxygens wiggling around on the carbon. You can't just have carbon by itself. So apparently we not only have carbon-free sugar, we also have oxygen-free carbon dioxide. Now, people say, oh, okay, Chris, you're just being, you know, obtuse about language. Well, I'm in an applied mathematics department, and we really are very interested in, you know, having unambiguous language. It helps people think. And a lot of this stuff has been confusing in many ways. And, you know, do you think that this can confuse people? Abso-damn-lutely. Look at this. The impact of oxygen-free carbon dioxide. This is an op-ed written by a certain individual who's been picking on Willie lately. So it says here, we are familiar with this effect in a car that is sat in the sun. The interior becomes hot because the carbon in the glass keeps the heat in. So, you know, this was written in 1990. So what I'm really trying to say, I mean, I'm not trying to actually just pick on this guy. Well, a little bit maybe, but, you know, is that, especially because the fact I wrote him a letter about it, this was in 1990, to his University of British Columbia address saying, this is not right, you know, and he never responded. So, well, maybe he might just get around to it one day, but so whenever I can, I always bring this up in climate talks I give. In any event, this is just absurd, and I'm just going to explain why. I mean, the whole idea was the vibration rotation spectrum in molecular spectroscopy. You need the oxygen hanging around, and it's not because of the structure of the glass. You can have greenhouse without carbon at all, or even without glass. You could have just opaque material, but let me get to that in a moment. I just want to talk about the greenhouse, since that's what we're really getting into. You probably have all seen this schematic. The sort of darker arrows over here are solar radiation frequencies, and this is infrared over here. And you notice down here, there's the little rinky-dink little arrows down there. Well, they're matter. Well, in other words, they're fluid flow and latent heat and stuff. They're just these tiny little things here. And there's great big arrows here for radiation, for infrared radiation. So when people get talking about greenhouses, they say, oh yeah, radiation, big arrows, latent heat and sensible heat. Well, yeah, they're just little arrows. Well, the thing I want you to notice here is this big arrow goes up, and that big arrow goes down. So this is a net. And if you look in the fine print there, instead of 114 and 96, the difference is 18. So that's 5 and 24. So it's actually comparable. So this is an important point. So I'm going to show you the Essex corrective of this thing. Just hammer it out and put in a little arrow. So now you see the radiation and the other types of transport away from the surface are roughly in the same ballpark. I would even question the need to separate these into separate categories, because fluid flow from the surface is intimately connected with each other. The latent heat drives the dynamics, and the dynamics affects the latent heat in lots of ways, and I'm sure that Bill Gray will tell us a lot more about that. So what I'm going to do is I'm going to use this much simpler picture to tell you about the greenhouse effect. And again, this is an issue about lack of understanding of language and how blurred and confused the whole thing. So basically what we have from the previous diagram is solar radiation comes in. We get radiation and fluid dynamics, which are kind of about the same. Fluid dynamics, I'm including both types of evaporation as well as motion. So the overall magnitudes are about the same. So I'll show you now the greenhouse effect, as everyone calls it. And it looks like this. So this is a greenhouse effect. And here's the hand of God coming down and putting more carbon dioxide in. And this arrow gets all wiggly. And then people say, well, now we have climate change and everything else. And the idea, the metaphor of the greenhouse, this is what they teach in elementary school. So this is really a common way of looking at it. And this is so imprinted and developed that they even have created in the usual dialogue a kind of glass that has special properties so that it's transparent in the visible but opaque in the infrared. You actually will see this is completely unnecessary, because this isn't the way a greenhouse actually works. I'll show you now how a greenhouse actually works. There we go. What happens is you have the fluid dynamics, the boiling air, which is part of the natural convective atmosphere. It comes up and it boils up until it hits the ceiling of the greenhouse. It bangs into the glass, and that's as far as it gets. It's game over. And so what happens is we now have to have a restoration of balance of flow in both of these cases so that we don't end up piling up heat or just cooling off randomly. So we actually have to get some kind of rebalance. And people say, well, this is just balanced flow in either case. So Chris, what's the big deal? Why do we care about this? And everyone calls it the greenhouse effect. This is the reason why it makes a difference and why this is an entrance down the rabbit hole. This is a completely certain outcome. Why? Because we completely understand the radiative transfer in this sense, that if you restrict the cooling at the surface, the air conditioning, if you will, due to fluid mechanics, then the compensation can be done in the radiation field. And the radiation, we know, is an increasing function of the temperature. So if you want more radiation out, the temperature's got to go up. And so we know completely certain that the greenhouse is going to get hotter. And in fact, you don't even need any kind of, it works for any kind of glass you want. If greenhouses get hotter, you don't even have to have them transparent. Even a tin box will get hot just because you've stopped the natural cooling at the surface. So this is an important thing to remember. This is a completely certain thing. Whereas this is a whole different ballgame. Because we're restricting the radiation flow, the compensation can be done by increasing temperature, or it can be done through the fluid dynamics. And the fluid dynamics is a different beast than radiative transfer in many ways. Unlike radiative transfer, it's not governed by the temperature. It's not run by temperature, it's driven by gradients. That's differences in temperature, differences in pressure. Those are the things that makes things go. And that's one of the reasons why I really like what Willie was doing in his talk. He talked about how they were using gradient fields rather than scalar fields, temperature fields, to see if they could get a handle on climate. And it makes sense because the gradients are what make things go. Now, I want to underline the fact that this is among the biggest scientific problems still existing in the world today. It connects with complex systems. It connects with all kinds of very deep problems. And I'll show you one of them just to show you how deep it does go. This is a web page, the Clay Mathematics Institute. This is their description of the Clay Millennium problems. And for solving any one of these problems, you get $1 million. So they're not just saying, well, we're a bunch of neurotic mathematicians and we think these are important. We're putting our money where our mouth is. We're putting a big pile of money on it. And you can do it. And you can see down the list, there's all kinds of them. The Poincare conjecture was just recently solved by a Russian mathematician. And I could go into that story in some detail because I know somebody who knows him. He actually turned the $1 million down. He just said, I don't want your damn money. I mean, he's my man, you know. I just thought he was cool. He turned it down. And he didn't actually publish the work. He just put it on the internet, and he didn't have any students. So actually, he would never get funding in any granting agencies. It's a kind of interesting thing, and I torment people in Canada about that. Anyway, but above this, you see the P versus NP. This is the whole computational complexity thing. Yang-Mills, that's high energy physics, and I mean, I'm not going to go into big detail here, but here we have the Navier-Stokes equations. These are the fluid dynamical equations that we're talking about that govern the air conditioning at the surface. So you can see this is a big deal. If you actually look at the details here, the Navier-Stokes equations, we're talking about just being able to solve them. We haven't actually solved the Navier-Stokes equations. These are the ones we use to predict the future, and we don't actually have a solution for them. Well, you can put it on a computer, and I'll talk about that in a moment, and that's really where we start heading down the rabbit hole in some ways. But it's important you mark that. And so let's go ahead to the next slide. So we have two equations, not just that one, two major unsolved fundamental problems of science. So this is the Navier-Stokes, and this is the one I mentioned at the beginning. This is the famous Reynolds averaging of the Navier-Stokes equation to try to solve the problem of turbulence. And basically, you have this extra term, and nobody knows what to do with it. And if you're an engineer, what you do is you take your system, you put it in the lab, and you figure out some empirical way to work this thing, and then you get a pretty good idea. But of course, if you have this sort of thing going on with climate, there's no laboratory to stick the Earth into. And so if you have that kind of closure problems, it's very difficult to do it. So here I have this fellow I met who was solving the closure problem all the time for policymakers. Okay, they said, well, we'll just put it on a computer. Okay, so this is now where we get into the real art of the computing. This is James Cameron's computer water versus real water. Now, the whole business, this is a real problem for all of us because we can go to movies and we can see these things that look so good, you know. Have we really solved the water problem? I mean, just look at this. This looks like real water to me. I mean, I just think, so we can do this on a computer, so what's the problem? Can't we predict the future? Well, if you kind of go around to the other side of the ship and you go back here, you notice that there are two wakes. If you're a fluid dynamicist, you'd be rolling on the floor now, right? This doesn't make any sense. This is just sort of an example of what you're saying. You can do anything you want. I mean, with a computer and with its computer graphics. The only goal of Hollywood is to make things look good. They're not able to actually predict things and to actually have a complete handle on the physics. So this is the Hollywood effect. And I call it cultural physics. And you can see examples of cultural physics, which I think are really fascinating. You see this is an explosion of the Death Star. And in the later versions of this, George Lucas decided he wanted to break the symmetry and have this two-dimensional ring going out. And I never did understand what that was for, but it was interesting how contagious it was, because here is the destruction of the Klingon homeworld, which was also a two-dimensional explosion. And the Lucas effect on Stargate also had this ring. It became very popular, but of course it's not physical. So just because something looks good doesn't mean it's great. And what I want to do is I want to now get into the nitty-gritty of computers, and I'm going to use a Hollywood movie to give you a feeling for that. This is a movie I was thinking about is The Truman Show. This is what comes to mind when I do this presentation. This was about some guy who lives in this completely artificial world, and he doesn't know it. And then one day he gets the feeling that something's not right. He steals a sailboat, sails across the ocean, and then he bumps into the sky where he finds the fake clouds painted on the wall. And that's actually what's happening in real computers. It's a fake world in many ways. Now, I have this graph here, and this is what I'm showing you is based on a paper that I did with some colleagues called Numerical Monsters. And there's a red dot there. That's what would happen if you had perfect computing. So I'm just going to stop this for a moment, and I'm going to run this MATLAB program. And this is the image that I want you to see. And you can ignore all the rest of it. You can see, forget about all of that. Look at this down here. Instead of getting a little red spot, which we saw originally, which was the zero error, you get this. You get 2,000 calculations, and they're random systems. And we solve them, and then we take the error, or take the solution in, and that numerical solution, we put it in, and what you initially see is you just see this cloud. It looks like random points, and if you zoom in on it, which is what I wanted to do, and forgive me, I'm sorry, I can't do it. It seems to want to crash on me. What you see as you zoom in is this cloud resolves into these streets, and the blue dots and the red dots are working on the same system but using a different numerical technique. And so you have basically 4,000 points that you're looking at, and some of them are off screen. But you can see basically that all the errors fall on this grid work, which we call the city streets monster. What the important takeaway here is, and this is what's going to come in a few minutes, is that the error is not random. This is a really important thing, is that it's structural, it's not random. It's just like we've gone, like the Truman Show, to the edge of the wall, and we see the fake clouds. This is the fake computation that's going on in between. Okay, so now that I have revealed all of my secrets here, we will press on past the Truman Show and say, well, what are the consequences for regular calculations? And here's one which I think is quite fine. This is a little numerical calculation, which mathematically tells you this. You get the value 1. Everyone can see that. This is what happens with a computer. And you'll see that you get, well, you don't get these black triangles there. I was just getting frisky and put them in, okay? So you see this jagged here, and then it drops down to 0, and then you get this jagged here. You get extra points if you realize that these teeth here are hyperbolas. You can figure those out. And if you can explain why it goes to 0. And you get bonus points if you can figure out why it's not centered on 0. This is the fun thing that numerical wants to do. So I'm not going to spend a lot of time on it. I'm just trying to illustrate the consequences of this is known as the finite representation of a computer. There's only a finite number of numbers in a computer. This is one version of 0. This is also 0. And this is a different 0 on computers. And you see this kind of like chalky, crayon-looking stuff. That's real. I mean, it's actually clumping in funny ways. And if you take this to a numerical analyst, and I know many of them, they look, I don't know why it does that. I mean, so it just, because this is like anti-numerical analysis. The usual numerical analysis is to reduce the error, whereas these numerical monsters are to make the errors bigger, right? So it's the opposite. So that's the beginning and the little warning and the notion that this is not random. It's very structured in a kind of random way. Now here's another consequence of having a finite representation, which is, everyone knows about this. This is the fact that the data you have or the images you present are pixelated. So here's the lady's eye, and you can make the eye bigger, and eventually you don't even recognize what's the eye, and that this is an image of an eye. The thing that is really interesting is what goes on in between the pixel points. And that's one of the things that's very important, is the distinction between what you can say on the pixels and what goes on in between. And that's important to mathematics. And the result is that when we teach people how to use computers in applied mathematics and in engineering and so forth, we have a kind of notion of what proper computing is, where we take the distance between these pixel points and we try to make sure that we choose the distance between the pixel points small enough, which is our grid size, small enough that it's smaller than the wiggles in the solution you're going to get. So the wiggles are this big, you want the solution, the grid points to be much smaller. But here's a remarkable thing. In geophysical computing, the grid points, in fact, are further apart than the wiggles. And this is a common problem, and it's a problem in fluid dynamics in engineering as well. And of course, they solve this problem by putting it into an experimental device, and they actually kind of make empirical formulas to get around this and sort of problem solve. But we can't do that with climate models. Which brings us to the question of turbulence and turbulent flow. This is an image by Leonardo da Vinci of flow of water falling into a container of water, and you can see all the whirls. And this is one of the ideas of turbulence, that you have whirls in the fluid, which includes air, and then those whirls break down into smaller ones and smaller ones and smaller ones. And it's called a Kolmogorov cascade or energy cascade. There's many terms for it. And then eventually the little wheels within wheels get small enough that the inertial properties and the viscous dissipation tear them apart and they can't exist anymore, so you don't get any more whirls. And so that bottom end is called the Kolmogorov microscale, and the atmosphere, it's about 1 millimeter, right? So that's the size that you'd have to have your grid on the Earth to make it so you're doing proper computing. So does anyone want to hazard a guess? I always love to do this. If I want to, say, compute 10 years in the future, and I want to do proper computing with, say, a 1 second time step, something comparable to 1 millimeter, how long do you think it would take contemporary computers? I'll just take a couple of guesses. I mean, yeah?
10 to the 34th power.
10 to the 34th. Anyone else?
4.6 billion years.
4.6 billion. Okay, one more. What? One more. No.
It's physically impossible, because it would use up more energy than producing the universe.
Oh, well, we're not going to think that. We're theoreticians. We don't worry about that. Okay. And one more estimate for how long it would take a modern computer to do 10-year forecast.
6 times 10 to the 23rd.
Okay, all right. So let's go to the blackboard now. So we'll go to the blackboard, and we have the number of locations with a millimeter grid, the number of times over 10 years, and we figure 10 variables. That's 3 velocity variables, pressure variables, you know, et cetera. You know, so gradients, so 10 variables is a good number. And then we take the floating point operations that we have available per year, and then we divide through, and we come up with a figure of 10 to the 20 years. So some of them were not bad, actually, you know. Usually people think it's pretty amazing when, you know, you have like well, it takes 30 years or something like that, but 10 to 20. So just think about that for a minute. Even if you increase the computing power by 1,000,000 or a gazillion, you know, 10 to the 20 years, that's still 10 to the 10 times the age of the universe, just for one 10-year calculation, right? So that tells you something. It tells you that if I was making a climate model, I'd have to make some compromises. Okay? And what happens is that you obviously you can't have a millimeter grid. I mean, there'd be problems, and we wouldn't be able to move, you know, with a millimeter grid. But we can't have that. So we have to have a much bigger grid size. And when I was a postdoc, the grid size was about 1,000 kilometers, but they've nailed that down to hundreds of kilometers now. Now the problem is there's a lot of physics, a lot of energy that's involved on scales smaller than hundreds of kilometers. And so the only way in which you can make anything that's even remotely sensible out of this is if you do something called fake physics. They're called parameterizations, that's the polite word for it, but fake physics, where you just take some data and you draw a line through it and say that's much easier to compute the line than some differential equation that goes with it, and things like that. And there's all kinds of, there's a whole industry involved in making the correct fake physics. It'd be a little bit more polite in French, faux physique or something, I don't know. But the interesting thing is that this, a whole thunderstorm, for example, are too small to show up. So you're like millions of thunderstorms every year, and they're all part of the fake physics. So in fact, almost everything involved in the energy transfer from ground to space is pretty much fake physics, and that's just about everything, right? So what it means is that climate models are empirical models, and this is something that many people don't understand. But people somehow are solving the closure problem over and over again. And many academics don't understand this. And you often get very distinguished individuals, such as these two, saying things like global climate models are based on the laws of physics. They make no assumptions of climate constancy or inconstancy. Over here, we have based on well-known equations of momentum, mass, energy, and equation of state. So their idea is that a climate model is you open up the lid of your climate model Cuisinart, and you take the equations and you dump them in and you close it and push them in a little bit, and you push the button and out comes perfect solutions of the future observations. And there are a lot of people who think this, and it's completely nonsense. Now I want to take on this issue of energy, and it's another consequence of the finite representation of, because we've heard of this is a third type of error that computers make. One of the things many people don't understand is that on a computer, the computer scheme that you use is different than the actual equations. So if these are the actual equations here, don't worry about the details. And it's really like an egg, and to put it on a computer, you have to crack the egg, you have to wreck it. And you put on what's known as a discrete map in place of the actual continuous differential equations. And that's a very important step, because when you move from here to there, this is a dynamical system, and this is a completely new independent dynamical system, which hopefully is not too different for a little while than this one. And that's, of course, the idea. This is a very poor numerical scheme called the direct Euler method. And this is equations for a simple harmonic oscillator. So you can imagine your grandfather clock and the pendulum. This is what this is describing, and this is the Hamiltonian. This is the conserved quantity for this. That's the energy. But this is the numerical scheme, and you can see the energy's there, but it's this other thing that's conserved. So this doesn't actually conserve the energy. Many people don't know that numerical schemes don't conserve the same things. It makes perfect sense. It's an independent system with its own mathematical symmetries, so it can't conserve this. Here's an actual output. So here you have the Hamiltonian. So you can see that the energy of this numerical system is actually increasing over time. So imagine what that means. If my arm is the pendulum of the grandfather clock, it's swinging and it's getting bigger. And it's just gaining energy, And this is the thing with something else that's conserved. And this is another thing, because there are methods that you can use called symplectic methods that will conserve energy. And so people work very hard on doing that. But the problem is that some of my colleagues and I have been able to show that for a second order system, you'll have two conserved quantities. You can show that, that if you can come up with a numerical scheme that conserves all of the quantities correctly, what you will have is tantamount to an exact solution of the differential equation. So if you're doing an exact solution of the differential equation, why not just solve it? Well, in the case of the Navier-Stokes equation, we don't have a solution, as I pointed out. So now the plot thickens because, well, I just first mentioned that because it's a partial differential equation, the number of conserved quantities are going to be infinite. But suppose you have a scheme that conserves all of the infinite conserved quantities and everything is fine, then you know what that means, because it's tantamount to an exact solution. That means $1 million, right? So here's an important point, that the numerics, the difference between numerics and the actual ability to solve the actual problem leads us straight to the fundamental problems that we're talking about. So it's very important. I want to talk about some more consequences of this. I just illustrate an example of instability. Here's a differential equation. Here's the exact solution, which we can compute. It's a linear, and this is what I wanted to use as a linear one. You run this thing, and you see this is the numerical scheme. You can see that they just run right on top of each other. And then eventually the blue one, which is the numerical scheme, just goes south. It just, adios, I'm gone, right? I mean, that's basically what happens, because somewhere the rounding error picks up a little bit of this positive eigenvalue and it's gone. And this is just even in the linear system, never mind the nonlinear system. So for a long time, people believed that things were inherently, computation was inherently instability making. But my colleagues and I, we wrote a paper in the 1990s in which we actually took a chaotic system, which is inherently unstable, and we used a numerical method to kill off the chaos. So in fact, it became a perfect harmonic oscillator. So this is over-stabilization with a numerical method. So you can do both. Now, why am I bringing that up? Well, now we come back to climate models. Okay, so here's a climate model. This is what's known as a Fourier power spectrum. It's kind of run backwards because meteorologists like to talk in periods instead of frequencies, but that's okay. What's really important is this comes from the fourth assessment report, 2007 of the IPCC. And you can see this wide range of different outputs from different models. And you can see there's a rather huge range in the actual magnitude of the power spectrum. So it's like, this is a logarithmic scale, so you've got orders of magnitude here difference. That's not what's important. What's important is this bit here. And you can see it's completely flat, flatty, flat, flat. And what that means is there's a theorem in mathematics, which is called the Wiener-Khinchin theorem, which says that if you do the power spectrum of a completely flat result, you'll get basically a completely flat output, or there's uncorrelated. So each value is uncorrelated with the next. So for a model, we expect then that what you'll get is this level, little bit of wiggling, modulated with some wiggling, but you just get this level signal for 1,000 years. And I think that Fred was talking about that earlier when he talked about the output of this model that they chopped up, that the unforced model should be completely flat. Whereas an observed variable, you see that you get the wiggle, but it kind of has long-term ups and downs. So that means that the models are incapable of exhibiting this kind of behavior on their own. Now, why has this happened? Well, one of the things that happened with climate models when I was at the Climate Center was that we had this thing called climatological drift that they were fighting against. That's where the whole atmosphere in the model just kind of was losing mass. The mass was just kind of dribbling away and nobody knew where it was going. It was just kind of, there's less and less mass over time. So then you see in the 2007 fourth assessment report, you can see little hints in the earlier drafts about struggles with negative densities and things which are typical of computation. I mean, these are kinds of things that they don't really want to have. So what you're writing is with one of these numerical complex systems, and you're trying to integrate it, not just for like an hour or 2 hours or a month. You're talking about integrating it for decades. The instabilities that kick in is like riding a Bronco. I mean, you're just jerking around. It wants to do all kinds of wild stuff. And so what they did is they are fighting for years and years instabilities. And one of the things they were crowing about in the fourth assessment report is we have got fake physics that now no longer requires us to stick in controllable arbitrary fluxes. They're called flux adjustments. They just sort of put some energy flows in there just to keep the Bronco under control, right? I mean, just so it doesn't go wandering off doing weird stuff. So their big accomplishment is that they didn't have this instability. What they defeated is the instabilities. But the question is, what does this real long-term behavior over those long time scales? If you go back to that image, you can see this is 100 months to 400 months, it's like up to 30 years. And you can imagine as you go further, multi-decadal, century time scales, what does it actually mean? Does it mean that we understand the climate in that time period? No, it doesn't, because we don't have empirical data over that long enough time scale, I mean, or at least not very much, that we can actually even tune the models to see what they're going to do over that time scale. And we also don't have the theory for this. And so this is a really important thing to understand. We don't know how to look at it on those time scales. So here is this middle row here is the world of our experience, our day-to-day life. And you can see this is a time scale of about a second, a length scale of about a centimeter. And you can see this is the molecular world, and this is the climate world. And you can see the scale from going from kinetic to the world of our experience to climate is about the same. So if you were a creature living on those timescales, I always call this, I give this person a name, a creature. I call the creature Larry Longwave. Suppose you were Larry Longwave, you would look at us as like we look at molecules. So it was something completely removed from our normal experience. And very recently, there's been a fad on the internet. Well, some artist design people did something really amazing. What they did is they created very long time exposures. This is a time exposure, which they do with a pinhole camera, and they have a bunch of photographic paper that they put inside, and they just let it sit for like 6 months. This is a 6-month time exposure of the world. It looks very muddy and kind of artistic in a way, which of course is their attraction. But I thought this is what Larry Longwave would do when he was on a vacation. He'd take snapshots. Like this would be a snapshot for Larry Longwave. And what you see here is this big arch in the sky. Well, that's what the sun looks like on this long time scales. And each one of these lines is the rising and setting of the sun. And some of them are missing and some of them are dotted, which just means that sometimes it gets cloudy, right? So you lose the sun sometimes. You could probably not quite make it out, but you notice that this street here on this bridge is empty. There's no traffic anywhere of any kind. It's completely steady. And so I imagine what would happen if Larry Longwave decided that he wouldn't just take snapshots, but he would take a movie. So he'd take one after the other, and he'd make a movie. It might take him a couple thousand years from our point of view, but just a short video from his point of view. And what would he see? And that's the interesting thing. And you could look at the sort of molecular aspect of this thing. Here's another shot by another person, Tarja Trigg is her name. You can see the same thing, the same arch in the sky. What you would see then with the movie is you would see that each successive thing would have a different configuration of dark and sunny days. So this arch would twinkle. It would be kind of glittering in the sky. The streets would stay empty because traffic is too quick for us to see. But the remarkable thing is the parking lots are full. And they're not full with cars, they're full with recurrent cars, recurrent visits of cars. So the movie probably those would be kind of shimmering as you saw. This would be a little bit like us looking at molecules. You wouldn't actually say, well, I've got this carbon dioxide molecule. Sometimes maybe the one oxygen will get kicked off and another one will come and replace it. And you might miss that whole transition, so it's not a particular identity. So there's a little bit of that going on here. So you can see this is the kind of world. And the question I have for this flat power spectrum stuff, which really deadens the behavior of long-term natural variability, which is what I'm really talking about. And Fred talked about that a little bit, and he said, well, he kind of favors external forcing. Well, my thinking on it is that you probably have both things, and you can't really tell one from the other unless you understand the internal natural variability. And this overstabilization, which I'm pretty confident about, I can't prove it, but they can't prove it either, is that they have overstabilized their models and that this flat behavior is completely spurious. And this is something that in many respects, I think is a central problem of the climate problem. It's a theoretical problem, and it's something that they cannot fix. And so I often say when I see various suggestions like Fred and Willie and so on, well, you see this climate model doesn't line up and so forth, and my usual advice is, don't tell them, they'll fix it. It's empirical models, you can just tune them up and it'll fix it. But this is a problem they can't fix, because we don't live long enough to have that kind of data, and we don't have the theory at this point to do it. And the problem is that the way in which funding has worked and so forth is to completely kill off, is to have some guy sit down and say to me, well, this isn't useful for policymakers, so why should you be doing this? And so this stuff doesn't get funded at all. No one does any research in this kind of very basic kinds of research and understanding it from that point of view. So we now come back to the Red Queen, and you saw this image already, and I'm sorry that my demo didn't work. But anyway, here we have the list: solving the closure problem, computers with infinite representation, computer, water, and cultural physics, greenhouses that don't work by the greenhouse effect, carbon-free sugar, oxygen-free carbon dioxide, non-existent long-term natural variability, and non-empirical climate models that conserve what they're supposed to conserve. And just getting started too. Well done, Alice. Thank you very much.
On the first global circulation model, which is over 40 years ago. And a thing that came out very quickly was, or theoretically, from the Russians was this predictability problem. For a three-dimensional flow, you could estimate that a weather model should be good for maybe a few days or a week. The two-dimensional flows like the Earth for maybe a month. Was sort of the theoretical limit. So there's a limit that chaos sets to the predictability of these flows, but I never saw a subsequent derivation that predictability actually set a limit to what you could get for climate. For predictability of a flow, it's true, but I never saw.
Well,
our problem was, when you went to long terms, you got the wrong climate. But that wasn't necessarily due to predictability, it's just due to bad physics.
Well, I agree with you.
I'm just asking if there's progress.
Well, I think what's happened is the way the political dynamics has probably set us back a generation on issues like that. So, I mean, that's basically my short answer to that. But the issue of whether it's possible to predict climate, I consider that an extremist statement that the IPCC said, which is impossible to do. It might be possible, but nobody knows how.
That's a misnomer. The theory shows that it's impossible to predict weather beyond a few days.
Yeah, no, yeah, but
climate,
bear with me here. Yeah. The problem is that it's really hard to even define. From a mathematician's perspective, to be rigorous, it's fine to say, oh, we average things, okay? But what do we average? Because you can average different things, and sometimes your average will give you one kind of behavior, a different kind of average. You have the closure problem. You don't actually end up with closed equations. There's reason to suspect, we already know that in nature, various kinds of averaging schemes have worked, but even if you go from kinetic theory to the regime of our experience, there are different ways to average, and some work and some don't. And there are dead ends. And just because someone is doing things like time averaging of fluid dynamical equations, we already know it didn't work for Reynolds. Why do we think just by increasing the time scale it's going to work? There's another classical kind of averaging, which is the averaging of field quantities. I thought it was really interesting that Willie was talking about let's talk about gradients for a change instead of just scalar values. And the third type of averaging is ensemble averaging, where you do what Fred was talking about, and that's problematic. I published a paper on what's wrong, and that ties in with this problem of these invariance quantities of what you're having with the numerical method versus the actual equations.
Thank you.
Okay.
Applying the mathematics to the medical codes, George Gilder had said that since each patient is different, it makes codes inoperable. I think that's the term Howard Maccabee used. Would you comment on the attempt to use a code number to describe a diagnosis in an individual patient?
No.
Thank you.
Yes.
This is remarkable. I really enjoyed your presentation, and now I begin to understand what's been happening. So my question is, what's going to happen? I mean, how long can this go on? I mean, this Alice in Wonderland. How do you see it playing out?
As long as humans, look, we're dealing with humans here.
Yeah, I realize
and
that.
they do weird things, and it takes a while for them to kind of get over it. And
So is it 10 years, 50 years?
Well, I mean, there are different schools of thought on it. I think it's already starting to run out of gas. I mean, I think that we're fortunate that the economic situation is the way it is. I mean, if we had a lot of money to burn, we'd be talking a lot about this. I don't know if that's fortunate, but anyway, I mean, it's still, I think that's certainly affected things. We had the ClimateGate thing, which incidentally, I don't know if you know, but you know, Ross McKittrick and Steve McIntyre tried to get the data originally, and that's how the ClimateGate broke out. And then someone released these emails. And the curious thing, just to give you an idea of how the world really works with humans, is that the anti-terrorist squads came to visit Ross and Steve to interview them about who released these evil emails. So it's like straight out of Kafka, you know. I mean, they were asking a legitimate academic thing. And so, I mean, I don't know how to fix that kind of thing. It's just craziness.
So will it, so you think it'll devolve just because of the money and just... So what will happen
I think all of this
afterwards?
stuff runs its course. I mean, I think the only reason why it's staying the way it is that there are a lot of people who invested their lives and careers into this for a long time, and there's a natural time scale for which these people are going to, the hard cases are going to hang on to it. But I think that the overall momentum is gone, and they're not going to be able to gin it up again quite the way they had.
So what do you think would follow after it falls apart?
Some new madness. Yeah, I mean, we're dealing with humans here, you know. I mean, yeah. Okay.